Summer, 1943. Rechlin Airfield, northern Germany. Test pilot Hans-Werner Lerche climbed into the cockpit of a captured Republic P-47 Thunderbolt. The massive American fighter sat on the tarmac bearing fresh German markings, a swastika painted over the white star that once adorned its fuselage. But it was what lay beneath the cowling that had brought Germany's finest aeronautical engineers to this remote testing facility. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. The Pratt and Whitney R-2800 Double Wasp, 18 cylinders, 46 litres of displacement, 2,000 horsepower. Lerche pressed the starter. The engine coughed, backfired, belched smoke, then roared to life with a sound unlike anything in the Luftwaffe's inventory. Through the vibration transmitted up through the airframe, through the stick in his hand, he felt the raw power of American industrial might. What he and his fellow engineers were about to discover would confirm their worst fears about the war they were fighting. The technological gap wasn't just about design philosophy, it was about an entire industrial ecosystem that Germany simply could not replicate, no matter how skilled their engineers or how determined their effort. The story of the R-2800 in German hands is not merely a tale of captured equipment. It is a story of the moment when Germany's technical elite confronted an uncomfortable truth. American industry had achieved something they deemed impossible. To understand what German engineers discovered, we must first understand what they were working with. By 1943, Germany's most powerful operational radial engine was the BMW 801. This engine powered the formidable Focke-Wulf 4190, considered by many to be Germany's finest piston engine fighter. The BMW 801 was no modest achievement. It was a 14-cylinder, twin-row radial engine displacing 41.8 litres. In its most common variant, the D2 model, it produced 1,700 horsepower at takeoff. The engine featured advanced systems for its time, including direct fuel injection, an automatic 2-speed supercharger, and the revolutionary Kommandogerät, an electromechanical engine control system that managed fuel mixture, propeller pitch, supercharger speed, and ignition timing through a single throttle lever. This early engine management system, a precursor to modern electronic control units, simplified pilot workload considerably and represented genuine German engineering innovation. BMW had pushed the 801's development as far as wartime conditions allowed. Experimental versions like the 801F achieved 2,400 horsepower, making it the only German aircraft engine type with a production-capable variant exceeding 1,500 kilowatts. But the 801F never entered production. The war ended before it could. In practical terms, German pilots in 1943 and 1944 flew fighters powered by engines producing between 1,560 and 2,000 horsepower, most commonly around 1,700. These were respectable figures. The BMW 801's power-to-weight ratio was competitive. Its reliability, once teething problems were resolved, was good. German engineers had reason to be proud of their work. Then they encountered the R-2800. The first P-47 Thunderbolt to fall into German hands largely intact arrived in early 1943. Others followed, recovered from emergency landings, retrieved from crash sites where the pilot had bailed out before complete destruction. By summer of that year, Rechlin had at least one flight-worthy Thunderbolt, and teams of engineers began systematic evaluation. The P-47 was massive by fighter standards. It weighed 14,000 pounds fully loaded, nearly twice the weight of a Messerschmitt Bf 109. German test pilots initially found it ungainly, its cockpit immense and unfamiliar after the snug confines of German fighters. The visibility was different, the controls had different feel, the entire machine seemed oversized. But when they pushed the throttle forward, all reservations evaporated. The R-2800 delivered 2,000 horsepower, not experimentally, not in carefully controlled test conditions, not with special fuel mixtures available only in laboratory settings. 2,000 horsepower reliably, repeatedly, operationally. and this was the early production version. By war's end, variants would exceed 2,400 horsepower, with experimental versions touching 2,800. The Germans captured the P-47 and immediately set about understanding how Pratt and Whitney had achieved this output. What they found both impressed and frustrated them. The R-2800 was an 18-cylinder, twin-row radial. Each row contained 9 cylinders arranged in a circle around the crankshaft. The total displacement was 2,804.5 cubic inches, or 45.9 litres. This was larger than the BMW 801's 41.8 litres, but not dramatically so. Yet it produced substantially more power. The secret wasn't size alone, it was execution. American engineers had solved the fundamental challenge of high-output radial engines, heat dissipation. When you pack 18 cylinders into a compact radial configuration and extract 2,000 horsepower, you generate tremendous heat. If that heat cannot be efficiently removed, engine components fail, pistons seize, cylinder heads crack, bearings deteriorate, oil breaks down. The cooling solution was elegant and sophisticated. Instead of cast or forged cooling fins, which had served adequately on earlier, lower-output engines, Pratt and Whitney machined the cooling fins, directly from the cylinder head material. This process created hundreds of thin, precisely shaped fins that dramatically increased surface area for heat transfer. The fins were integrated into the cylinder head itself, not added afterward, ensuring optimal thermal conductivity. German engineers examined these cylinder heads with magnifying glasses. They measured fin thickness, fin spacing, fin depth. They understood the principle. They lacked the machine tools and manufacturing processes to replicate it at scale. Here was the first uncomfortable reality. The R-2800's performance wasn't achieved through revolutionary theoretical breakthrough. It was achieved through manufacturing excellence. The difference between German and American engines wasn't primarily conceptual, it was industrial. The engine's construction revealed layer upon layer of sophisticated manufacturing. The crankshaft, the massive component that converted the piston's reciprocating motion into rotational power, was a masterpiece of metallurgy and machining. It had to withstand enormous stresses while maintaining perfect balance. American manufacturers produced these crankshafts with tolerances and material properties that German industry struggled to match under wartime conditions. The supercharger, which compressed incoming air to maintain power at altitude, employed advanced impeller designs and high-speed gearing. The two-stage supercharger system on later variants represented mechanical complexity that required precision manufacturing and quality materials. Again, German engineers understood the theory. Implementing it while maintaining reliability proved far more challenging. Then there were the bearings. This seemingly mundane component revealed perhaps the most frustrating gap. Engine bearings must support rotating shafts under tremendous loads while minimizing friction. They must endure high temperatures, contamination from combustion byproducts, and constant mechanical stress. Bearing failure means engine failure, often catastrophically. When German metallurgists analyzed bearings from the captured R-2800, they found something puzzling: traces of iridium in the bearing metal. Iridium, a precious metal from the platinum group, appeared as what they initially thought might be a contaminant. Further analysis revealed it was deliberate, though they couldn't immediately determine why. The answer lay in material science that Germany, despite its strong tradition in chemistry and metallurgy, had not pursued down the same path. American bearing manufacturers had developed alloys incorporating iridium and other elements that dramatically improved bearing performance under the extreme conditions of high-output aircraft engines. These weren't theoretical developments. They were production realities, incorporated into tens of thousands of engines. German industry couldn't easily replicate these alloys. The materials weren't available in sufficient quantities. The metallurgical know-how, while theoretically comprehensible, required extensive development work to translate into manufacturing practice. And most critically, time and resources were running out. The fuel injection system presented another revelation. While Germany had pioneered direct fuel injection in aircraft engines, the American implementation in the R-2800 showed different design philosophy. The system was robust, maintainable, and designed for operation by mechanics with varying skill levels. This wasn't just about making the engine work in a factory test cell. This was about making it work reliably in the field, maintained by 19-year-old mechanics on an aircraft carrier deck in the Pacific or at a forward airstrip in New Guinea, or anywhere the American military operated. German engines, by contrast, often required more skilled maintenance. The BMW 801's sophistication came with complexity. Its Kommandogerät system, while ingenious, needed careful adjustment. Field maintenance could be challenging. The American approach prioritized operational reliability over ultimate refinement. This reflected a fundamental difference in design philosophy shaped by different military requirements. Germany fought a continental war where damaged aircraft could often be returned to well-equipped rear area facilities. The Luftwaffe maintained a relatively small number of highly skilled maintenance personnel. American forces, operating globally across vast distances, needed engines that could be maintained anywhere by personnel with standard training. The R-2800's modular construction reflected this philosophy. Major components could be replaced in the field. The engine was designed to be removed and replaced as a complete unit, the power egg concept that Germany had also developed but implemented differently. American engines emphasized interchangeability and standardization to an extraordinary degree. Testing of the captured P-47 revealed another aspect of American advantage: fuel quality. The R-2800 was designed to operate on 100-octane aviation gasoline, later upgraded to 130-grade fuel. This high-octane fuel allowed higher compression ratios and supercharger boost pressures without detonation, directly translating to increased power output. Germany's most common aviation fuel by 1943 was B4, with 87-octane rating. The Luftwaffe's highest-grade fuel, C3, used in late-war high-performance engines, roughly equaled Allied 100 to 130-grade fuel, but production was limited. Germany's synthetic fuel program, necessary due to lack of natural petroleum reserves, struggled to produce high-octane fuel in sufficient quantities. The fuel situation was both cause and effect of the performance gap. American engines could achieve higher power, partly because they ran on better fuel. But America could produce better fuel because it had access to natural petroleum and had invested heavily in refining technology. The Germans faced material constraints that engineering brilliance alone couldn't overcome. German test pilot Walter Wolfram, a Luftwaffe ace and recipient of the Knight's Cross, was among those given the opportunity to fly captured American fighters at Rechlin. His evaluation of the P-47 provides insight into how German pilots perceived the aircraft powered by the R-2800. During the war, I had the opportunity to fly captured P-47s, Wolfram recalled after the war. I didn't like the Thunderbolt. It was too big. The cockpit was immense and unfamiliar. After so many hours in the snug confines of the 109, everything felt out of reach and too far away from the pilot. But Wolfram's criticism focused on ergonomics and familiarity, not performance. The P-47's engine impressed even skeptical German pilots. Its power was undeniable. Its reliability, even running on captured fuel that sometimes didn't meet specifications, proved remarkable. The R-2800 kept running under conditions that would have troubled more finicky power plants. The broader testing program at Rechlin and other evaluation facilities revealed systematic American advantages. The Germans had also captured P-51 Mustangs, though these used liquid-cooled Rolls-Royce Merlin engines built under license by Packard. They tested captured P-38s with their twin Allison engines. They evaluated B-17 and B-24 bombers powered by Wright radial engines. A pattern emerged. American engines, regardless of type, displayed certain common characteristics. They were designed for mass production. They emphasized reliability over ultimate performance. They incorporated safety margins that German engines pushed to extract maximum power from limited resources, often lacked. They were, in short, products of an industrial system operating under fundamentally different constraints. Hauptmann Heinz Nock, another Luftwaffe pilot who encountered American aircraft, noted the implications. The Americans, he observed, didn't need the absolute best fighter. They needed very good fighters in overwhelming numbers, maintained by average mechanics, flown by adequately trained pilots, supported by limitless fuel and ammunition. The industrial equation favored quantity and reliability over individual superiority. By late 1943, German engineers analyzing captured American equipment faced an uncomfortable conclusion. The technology gap wasn't primarily about innovation or theoretical understanding. Germany's engineers were brilliant. BMW's Kommandogerät represented genuine advancement. German supercharger development was sophisticated. Fuel injection technology had originated in Germany. The gap was industrial capacity and resource availability. Consider the production numbers. Pratt and Whitney, along with its licensees, including Ford Motor Company and other contractors, produced over 125,000 R-2800 engines between 1939 and 1960. During the war years alone, tens of thousands rolled off production lines. Peak production reached staggering rates, with completed engines emerging at intervals measured in hours, not days. BMW produced approximately 61,801 engines during the entire war. This was Germany's most produced radial engine, and it represented a significant achievement under wartime conditions. But it was half the American output of a single engine type, and the Americans were simultaneously producing Wright Cyclones, Allison V-1710s, Packard Merlins, and numerous other engine types in comparable or greater numbers. The manufacturing infrastructure difference was even more dramatic. American factories had access to reliable electrical power, abundant raw materials, specialized machine tools, and most critically, they operated beyond the range of enemy bombers. German industry, by 1943, faced increasing Allied bombing that disrupted production, destroyed facilities, and killed skilled workers. The machine tools required to produce engines like the R-2800 represented their own manufacturing challenge. Precision lathes, milling machines, grinding equipment, measuring instruments all had to be available in quantity and maintained in calibration. American industry had invested heavily in machine tool production during the 1930s. By 1941, when war production accelerated, the infrastructure existed to rapidly expand output. Germany had strong machine tool industry, but it couldn't expand quickly enough to meet accelerating demands while simultaneously replacing equipment destroyed by bombing. As the war progressed, this bottleneck tightened. Even when German engineers designed improvements to existing engines or developed new types, translating designs into production hardware became increasingly difficult. The aluminum supply illustrated resource constraints. Aircraft engines require high-quality aluminum alloys for cylinder heads, crankcase, and numerous other components. These alloys must withstand high temperatures and mechanical stress, while remaining relatively lightweight. American aluminum production, supported by abundant electrical power and bauxite supplies, dwarfed German capacity. Germany's access to aluminum was limited, and the quality sometimes varied. When German metallurgists examined R-2800 components, they found alloys with consistent properties and excellent quality control. American manufacturers could afford to reject components that didn't meet specifications. German manufacturers, facing chronic material shortages, often had to accept marginal components or develop workarounds. The bearing situation exemplified the problem. Understanding that iridium-containing bearing alloys improved performance was one thing. Obtaining sufficient iridium to implement this across thousands of engines was another matter entirely. Iridium is one of the rarest elements in the Earth's crust. American industry had access to global supply chains, including platinum group metals, from sources Germany couldn't access after 1941. Substitute materials could work, but often with reduced performance or reliability. German engineers became masters of substitution out of necessity, developing alternatives when ideal materials weren't available. But substitutes meant compromises. An engine designed around optimal materials, then built with substitutes, would never quite achieve design performance. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. The testing program at Rechlin generated detailed reports. These documents, many of which survived the war, reveal systematic analysis of captured equipment. German engineers measured everything power output at various altitudes, fuel consumption, cooling effectiveness, maintenance requirements, component durability. They flew captured aircraft in mock combat against Luftwaffe fighters to assess performance characteristics. The conclusion was inescapable. American fighters, powered by engines like the R-2800, held significant advantages, especially at high altitude, where supercharger design and fuel quality particularly mattered. The P-47 could engage at altitudes where German fighters struggled. It could absorb battle damage that would down German aircraft, both because of the R-2800's durability and the Thunderbolt's rugged construction. More frustrating was that these advantages derived not from secret technology Germany might capture and exploit, but from industrial capacity Germany couldn't replicate. The reports flowing back to the Reich Air Ministry contained few recommendations for countermeasures. You couldn't counter an enemy's superior industrial base through tactical adaptation. The BMW 801F, which existed in prototype form and could have addressed the power gap, required resources for production that Germany couldn't spare. The turbocharger development that might have given German fighters high-altitude performance faced similar constraints. Projects were approved, prototypes built, but translation to operational hardware foundered on lack of industrial capacity. Albert Speer, appointed Minister of Armaments in 1942, attempted to rationalize German war production. He achieved remarkable results, increasing output despite Allied bombing. But Speer was optimizing an industrial base that was fundamentally insufficient for the war Germany was fighting. The R-2800 in German hands represented physical proof of this insufficiency. What made this particularly galling for German engineers was that they understood the theory behind American achievements. The machined cooling fins, the advanced bearing alloys, the sophisticated supercharger designs, none of this was beyond German comprehension. Given sufficient time, resources, and industrial capacity, German engineers could have developed equivalent systems. Time was the crucial shortage. The war was entering its decisive phase. Every month brought new American aircraft with more powerful engines. The P-47 evolved from early models with mechanical superchargers to later variants with turbo superchargers and water injection, pushing power output higher. The F-6F Hellcat and 4U Corsair, both powered by R-2800 engines, dominated Pacific skies. The P-61 Black Widow night fighter, the Martin B-26 Marauder, the Douglas A-26 Invader all used the R-2800. Germany faced a growing fleet of enemy aircraft powered by an engine it could analyze but not replicate. And behind those aircraft stood an industrial system capable of replacing losses faster than Germany could inflict them. American pilot training programs graduated thousands of aviators. American shipyards launched aircraft carriers in months. American factories produced aircraft at rates that seemed impossible to German planners who reviewed intelligence reports. The captured P-47 at Rechlin became a symbol. It demonstrated not just American technological achievement, but American industrial philosophy. The R-2800 wasn't designed to be the ultimate aircraft engine. It was designed to be a very good engine that could be mass-produced by workers with standard training, maintained in the field with standard tools, and operated reliably under combat conditions anywhere in the world. This philosophy extended throughout American military equipment. Tanks, trucks, artillery pieces, ships, all emphasized reliability and maintainability over individual superiority. The Sherman tank wasn't as heavily armoured as German tanks, but America produced 50,000 of them. The Garand rifle wasn't theoretically superior to German rifles, but it worked reliably in all conditions, and every American soldier had one. German equipment often achieved higher individual performance, but required more skilled operators and maintainers. This made sense when Germany expected short, decisive campaigns. It became a liability in a prolonged global war against enemies with superior industrial capacity. The implications extended beyond immediate tactical concerns. German engineers examining the R-2800 were witnessing the fundamental economic reality of modern industrial warfare. Victory would not be determined by which side had the most brilliant engineers or the most courageous pilots. It would be determined by which side could sustain production, maintain supply chains, and replace losses. The Rechlin testing facility, located in Mecklenburg in northern Germany, had become a clearinghouse for captured Allied equipment by 1943. Alongside the P-47 Thunderbolts, engineers evaluated P-51 Mustangs, B-17 Flying Fortresses, and various other American aircraft. Each provided pieces of a larger puzzle that, when assembled, revealed the scope of the industrial challenge Germany faced. The evaluation process was systematic and thorough. German test pilots flew the aircraft under various conditions: low altitude, high altitude, combat maneuvers, formation flying. Mechanics tore down the engines, measuring tolerances, examining manufacturing techniques, analyzing materials. Metallurgists tested component samples, determining alloy compositions and material properties. Performance engineers calculated power output, fuel consumption, and efficiency across the operational envelope. Every measurement, every test flight, every material analysis reinforced the same conclusion. The Americans had achieved manufacturing excellence at industrial scale. This wasn't about isolated examples of superior technology. This was about consistent quality across thousands of engines, each meeting specifications, each performing reliably, each maintainable by standard procedures. The cooling system alone represented a manufacturing achievement that German industry struggled to match. Those precisely machined fins that covered the cylinder heads required specialized machine tools operating at close tolerances. Any variation in fin thickness or spacing reduced cooling efficiency. Multiply this requirement across 18 cylinders, then across thousands of engines, and the manufacturing challenge becomes clear. German engineers calculated that replicating this cooling system would require retooling existing factories or building new facilities. Either option demanded time and resources Germany didn't have. The strategic bombing campaign had already forced German industry into dispersed production, spreading manufacturing across smaller facilities to reduce vulnerability. This dispersion, while necessary for survival, reduced efficiency and complicated quality control. By 1944, as Allied forces invaded France and Soviet armies pushed from the east, the lessons learned from captured American engines acquired bitter clarity. Germany couldn't build its way out of the strategic situation. Even if BMW had successfully transitioned the 801F into production, even if turbocharger development had succeeded, the number of engines Germany could produce remained limited by resources, manufacturing capacity, and Allied bombing. The bombing campaign's impact on engine production was devastating and multifaceted. Direct hits destroyed factories, obviously, but the indirect effects proved equally crippling. Factories were dispersed to reduce vulnerability, but dispersion reduced efficiency. A centralized facility could move components between manufacturing steps quickly. Dispersed production required transportation between sites, vulnerable to bombing and increasingly unreliable as Germany's rail network deteriorated. Skilled workers were killed in bombing raids or drafted into military service as manpower shortages worsened. By late 1944, German factories increasingly relied on forced labor prisoners of war, concentration camp inmates, conscripted workers from occupied territories. These workers, often malnourished and working under duress, couldn't maintain the quality standards that precision engine manufacturing demanded. Sabotage, whether deliberate or simply from lack of motivation, became an additional quality control problem. Transportation networks that moved components between facilities were disrupted constantly. A crankshaft manufactured in one location, cylinder heads from another, supercharger components from a third all had to reach final assembly. When rail lines were bombed or bridges destroyed, components accumulated at some facilities while others starved for parts. The logistics of dispersed production became a nightmare that German planners never fully solved. Quality control suffered as inexperienced workers replaced craftsmen. An experienced machinist knows by feel when a cutting tool is properly aligned, when material is removing cleanly, when tolerances are being met. Training replacement workers to this standard takes time. German industry didn't have time. The replacement workers did their best, but best effort often fell short of the precision aircraft engine manufacturing required. Synthetic oil plants, critical for both engine lubricants and aviation fuel, became priority targets that Allied bombers struck repeatedly. Germany's lack of natural petroleum reserves meant it depended entirely on synthetic fuel production. The Fischer-Tropsch process could produce gasoline and lubricants from coal, but the plants were large, complex, vulnerable facilities. Destroying them didn't just reduce fuel availability, it crippled the entire Luftwaffe operational capability. American engine factories, by contrast, operated at peak efficiency. Willow Run, where Ford produced B-24 bombers complete with engines, became a symbol of American manufacturing prowess. The massive facility, over 3 million square feet under one roof, employed tens of thousands of workers on assembly lines that epitomized mass production. At peak production, a completed B-24 rolled off the line every 63 minutes. Similar facilities across the United States turned out engines, airframes, and complete aircraft in numbers that German intelligence analysts initially refused to believe. Reports of American production figures were sometimes dismissed as Allied propaganda because the numbers seemed impossibly high, but they were real. The United States in 1944 produced 96,000 aircraft. Germany produced approximately 40,000. The German engineers who had examined the captured P-47 understood what those production numbers meant. Each R-2800 represented not just individual components, but an entire industrial ecosystem. The aluminum came from smelters powered by hydroelectric dams, massive installations like those on the Columbia River and Tennessee Valley that Germany could never replicate. The specialized steels came from mills with reliable coal and iron ore supplies, operating continuously without fear of bombing. The bearings came from factories with access to rare earth elements and platinum group metals from global supply chains. The fuel came from refineries processing abundant petroleum from Texas, California, and Oklahoma. Every link in this chain functioned reliably, protected by geography from enemy interference. The Pacific and Atlantic Oceans provided security that allowed American industry to operate without the disruptions German industry faced daily. This geographical advantage, combined with resource abundance, created conditions where American manufacturing could achieve its full potential. When German test pilots flew the captured P-47 against Luftwaffe fighters in mock combat, the results were sobering. At altitudes above 25,000 feet, the Thunderbolt held decisive advantages. Its turbo-supercharged R-2800 maintained power where German fighters struggled with thin air. The P-47 could choose whether to engage or disengage, climbing away from pursuers or diving to escape the classic advantage of the energy fighter. The aircraft could also absorb tremendous battle damage. The R-2800's rugged construction meant it could lose cylinders and keep running. Aircraft returned to base with portions of the engine shot away, still producing enough power for controlled flight. German pilots reported that P-47s they hit with cannon fire often kept flying, trailing smoke but refusing to go down. This durability derived partly from American design philosophy and partly from manufacturing quality. Components built to tight tolerances with quality materials provided safety margins that allowed continued operation even with damage. The redundancy built into systems meant single-point failures rarely caused catastrophic engine failure. Major Werner Mölders, who had tested captured Spitfires and Hurricanes before the Battle of Britain, once observed that British fighters were childishly easy to fly compared to German aircraft. This observation, sometimes quoted as criticism, actually revealed a critical difference in design philosophy. British and American aircraft emphasized ease of operation to accommodate pilots with varying skill levels. German aircraft often demanded more from their pilots, but rewarded skill with higher performance. In a short war with limited forces, the German approach made sense. In a prolonged conflict requiring tens of thousands of pilots, the Allied approach proved superior. Not every pilot could be an ace. Mass air forces needed aircraft that average pilots could fly effectively. The same principle applied to engines. The R-2800 could be operated and maintained by average mechanics with standard training and tools, making it ideal for the global war America was fighting. The testing reports from Rechlin documented specific technical findings, but the deeper message was strategic. Germany had entered a war it could not win through technology alone. The R-2800 was simply one example of a broader pattern. In every category, tanks, artillery, ships, small arms, vehicles, aircraft, American production outpaced German capacity by factors of 2, 3, 5, or more. German tank production for the entire war totaled approximately 28,000 vehicles of all types. American tank production exceeded 88,000. German aircraft production for the war totaled approximately 120,000 aircraft. American production exceeded 300,000. The disparities extended across every category of war material. Some German equipment achieved superior individual performance. The Tiger tank had better armor and a more powerful gun than the Sherman. The Messerschmitt Me-262 jet fighter was faster than any Allied fighter, but Germany produced only 1,400 Tigers and fewer than 1,500 Me-262s. Superior individual weapons couldn't compensate for overwhelming numerical inferiority. By 1945, as Germany's situation deteriorated, some of the captured American aircraft at Rechlin were pressed into emergency service. A few P-47s flew operational missions for Kampfgeschwader 200, the Luftwaffe's special operations unit that operated captured aircraft, but these were desperate expedients, not viable solutions. Fuel shortages meant even captured aircraft with full tanks couldn't fly regularly. Spare parts were non-existent. When something broke, the aircraft was grounded permanently. Pilots who flew these captured aircraft reported a bittersweet experience. The power and capability were impressive, even exhilarating, but flying an enemy aircraft with enemy markings painted over, knowing that Germany could never produce such equipment in necessary quantities, served as a constant reminder of the hopeless strategic situation. The final irony was that some of the most advanced German engine designs existed only on paper as the war ended. The BMW 801F, which had achieved 2,400 horsepower in testing, would have been competitive with late-war variants of the R-2800. The engine was approved for production. Tools were being prepared. But production never began. The resources couldn't be spared. The factories couldn't be protected. The time had run out. The Jumo 213, in development as a high-altitude power plant with advanced supercharger systems, showed promise in testing. The Daimler-Benz 603 achieved impressive power and was entering service in late-war aircraft. The Daimler-Benz 605, a further development, powered some of the highest performance piston engine fighters Germany produced. But promising and in development, and some meant little when factories were rubble and the Red Army was approaching Berlin. The engineers who had analyzed the captured R-2800 in 1943 knew by 1945 that their findings had been prophetic. They had identified a gap that could not be closed through engineering excellence alone. The gap required industrial capacity Germany no longer possessed, assuming it ever had, sufficient capacity for a global war against the combined Allied powers. After the war, some of these engineers emigrated, bringing their expertise to other nations. The United States, through Operation Paperclip, recruited German aerospace engineers. The Soviet Union similarly recruited German technical personnel. Britain and France sought German expertise for their recovering industries. The knowledge gained from studying American engines influenced post-war European engine development worldwide. Other German engineers remained and helped rebuild their shattered homeland, this time focused on civilian applications. The lessons about manufacturing quality, reliability, engineering, and design for maintainability became incorporated into European industrial practice. Post-war German industry, particularly automotive and mechanical engineering, earned worldwide reputation for quality and precision, applying the lessons learned in wartime to peaceful purposes. The R-2800 itself continued service for decades after 1945. It powered early airliners like the Douglas DC-6, which entered service in 1947 and flew commercially into the 1970s. Thousands of airline passengers crossed oceans behind R-2800 engines, usually without knowing what powered their aircraft. The engine flew in water bombers fighting forest fires, where reliability and power mattered as much as in combat. The Canadair CL-2-15 water bomber, which first flew in 1967, used R-2800 engines and continues service in some places today. This represents an extraordinary service life, an engine designed in the 1930s, still performing useful work in the 21st century. Restored warbirds at airshows worldwide still fly with R-2800 engines, more than 80 years after the first prototype ran. Enthusiasts maintain these engines, sourcing parts from remaining stocks or manufacturing replacements using modern techniques. The distinctive sound of an R-2800 starting the coughs, backfires, smoke, then the steady roar remains one of aviation's most evocative sounds. This longevity testifies to the soundness of the basic design and the quality of American wartime manufacturing. Engines built 80 years ago, stored properly or carefully rebuilt, can still produce rated power. The engineering was that good. The manufacturing was that precise. The materials were that durable. The story of German engineers confronting the R-2800 is ultimately a story about the nature of modern war. Technical sophistication matters, but industrial capacity matters more. Brilliant individual designs are valuable, but mass production of good designs is more valuable. The most advanced prototype means nothing if it cannot be manufactured in quantity, maintained in the field, and operated by typical personnel. German engineers in 1943 looked at the R-2800 and saw an opponent they could not defeat. Not because American engineers were necessarily more brilliant, though American engineering was certainly formidable, but because American industry operated at a scale and efficiency that Germany could not match under any circumstances, and certainly not while fighting a multi-front war against multiple opponents. The machined cooling fins, the advanced bearing alloys, the sophisticated supercharger designs, the modular construction, the emphasis on reliability. These represented an industrial civilization at full mobilization, leveraging abundant resources, secure geography, and established manufacturing expertise. That P-47 sitting on the Rechlin tarmac, its R-2800 engine now silent after a test flight, told a story that transcended individual components. It told the story of assembly lines in Connecticut and Michigan producing engines by the thousands, of freighters carrying those engines across U-boat-infested Atlantic waters, protected by destroyer escorts and aerial patrols, of mechanics on Pacific Islands, installing them in fighters preparing for the next mission against Japanese positions, of pilots who trusted the engine to bring them home through flak and fighters, and usually it did, even when damaged. The German engineers wrote their reports, filed their findings, and returned to the desperate effort to keep the Luftwaffe operational with dwindling resources. They knew what the R-2800 represented. They knew what it meant for Germany's prospects in a war that was increasingly obviously lost. They knew that understanding the problem and solving the problem were entirely different challenges, separated by an industrial capacity gap that could not be bridged. The war's outcome was never determined solely by the R-2800, of course. Strategic decisions, military leadership, alliance politics, geography, resources, and countless other factors shaped the conflict's trajectory. But in that one engine, in those 18 cylinders producing 2,000 reliable horsepower, lay a microcosm of why Germany could not win the industrial war it had initiated. When the Third Reich collapsed in May 1945, American factories were still producing R-2800 engines at full capacity. Production continued into the post-war period for civilian applications, eventually exceeding 125,000 engines total across all variants and all years of production. The German engineers who had examined captured examples in 1943 could have predicted this. They had seen the future in that Rechlin hangar, and it belonged to those who could not just design excellence but manufacture it at scale, sustain it logistically, and deploy it globally. The lesson transcended the specific technology. Industrial warfare rewards not the most advanced individual weapons, but the most effective industrial systems. The R-2800 was very good, mass-produced, reliable, and maintainable. That combination proved unbeatable. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now, and don't forget to subscribe.